So the next topic is what happens when you multiply or binary operate an element by itself again and again and again. So in a sense you get powers of an element. So interesting things happen when you do that, and it leads to the concept of the order, not of a group. Remember, the order of a group is its size, but the order of an element, which is a bit more subtle. But we're heading towards that once I clean this damn board. Okay, so now we're talking about, where are we down? We're getting close to the end before we get into problem solving time. Okay, powers of an element. So I'm looking for a dry spot. I'm trying to get the angle. So say you have an element A here, okay, and you binary operate on it by itself. So you get A little circle A, or we'll just call it AA. Now, even that's a bit tedious, so let's shorten this. So by definition, we'll just call this A squared. Right? It's just a notation. This is a new notation. So if you see A squared, all it means is this: A binary operator A on it, A on itself, binary operated. Okay. So now you could keep doing this, right? So you could have A cubed, and that by definition is just A. Now it's a group, right? So it's associative. So this is the same as this. In fact, you don't care about the brackets because of groups are associative. You can get rid of the brackets. So we'll just talk about A cubed, right? Now, you could go, you can keep doing this, so you could go to A to the n, and n could just keep going. But let's assume we're talking about a finite group, okay? Finite group. So this process of A squared, A cubed, and so on, A to the n, dot 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 dot. Common sense says this process cannot keep going if each result here, like A and A squared and A cubed, they cannot keep being all different. I mean, the result being all different. So imagine like A squared is different from A, and A cubed is different from these two, and A to the fourth is different from these three, and so on. Can you see that process, you cannot keep doing it indefinitely? Why not? I mean, if it just keeps going and every one is different, if it keeps going, you then end up with an infinite number of different elements, right? If each power is different and you just keep going, sooner or later you will have more different results, different elements than there are in the whole group, right? Because it's a finite group. Okay, so there's a limit. So at some stage you have to get an element. What do we call it? Let's call it S. Right? So at some stage you come to a power, we'll call it S, of A, where that result is equal to one of the ones before. So let's say it was here. So let's say, and that was at position R, let's say. Okay? Sort of common sense. You cannot keep going indefinitely and having each one distinct, different from all the others element. At some stage, as you keep going, you have to reach an element, some power that is the same as some other one, some earlier one. And let's say, so AS then is equal to AR, right? So let's say this is at position, the rth position. That's at the nth position, the third position, second, and so on. Right? This is at the S position. And let's say that's the first time that you get an element here. A to the S. That's A by A S times. Okay. So A to the S is A by A S times. So this, whatever this result is, it must be equal to, sooner or later, to one of the previous ones. So let's say the previous one is A to the R. So you have this. Okay? So that's true. All right. Now let's assume that S is greater than R. Okay. So A to the S minus R is equal to A to the R times A to the minus R. Now, can you follow that? Well, maybe I've skipped a step. Let me prove something. Now, A to the N times A to the N is just A to the N plus N. Right? Does that seem fairly obvious? Okay. So A to the N times A to the minus N is A to the N minus N. So just the usual exponent type properties. All right. Okay. So if I multiply on the right by AS times A to the minus R, I'll get A to the minus R. So A to the R, A to the minus R, and that's the same as A to the R minus R, and that's A to the naught. Now I haven't done that. Like this is to the 1. Now A to the naught, that's new. You define that to be E, right? Your unit. So what I've got here is that A to the S minus R is E. Okay. Now let S, just rewrite S minus R as some other integer k, because we've assumed this, right? S is greater than R. So let's just relabel S minus R as k. So that means that A to the k is E. Okay. All right. So now we can define what the order of an element, not the order of a group. That's something else. That's the size of the group. The order of an element is the smallest positive integer k, so that A to the k is the unit. Okay. So this number here, if it's the smallest one, and you could have larger ones, but if this is the small, the first time this happens, right? When that's the first time that this equaled that, A to the S equals A to the R, and so this k here is the smallest integer, such that A to the k is the unit. Now you could have like A to the 2. Yeah, watch. So you had A to the 2k. That's still E, right? Why? Because A to the 2k is just A to the k, A to the k. And that's EE, which is E. And EE. Right? So I'll say it again. The order of an element, it's distinct from order of a group. The order of an element is the smallest positive integer, k, so that a to the k is e. Right? That's how you define the order of an element. It's the power that you have to raise a by, the element, by, to get e. Right? That's the smallest positive number that does that. That a to the k gives you e. That k there, by definition, is the order of an element. Okay? Alright? I think I'll stop there for reasons of practical reasons on my filming.